Good morning, everybody, and welcome once again to the JKMRC Friday morning seminar series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we'd like to acknowledge the Turrbal and Yagara people as the traditional owners on the lands on which we meet today. We pay our respects to their ancestors and their descendants who continue cultural and spiritual connection with country, and we recognise their valuable contribution to Australian and global society. My great pleasure today to welcome Mr. Len Kolff. Len is the Head of Business Development and the Chief Geologist for Atlantic Lithium and has worked in minerals exploration for over 25 years. Len was instrumental in the discovery and evaluation of the Ewoyaa Lithium project in Ghana, the Mofe Creek iron ore project in Liberia, and Simandou iron ore project in Guinea, and the Northparkes Copper-Gold deposit here in Australia. Today, Len will be presenting on the discovery and evaluation of the Ewoyaa Lithium Pegmatite project and discussing lessons learned in the relatively new field of hard rock lithium exploration in deeply weathered tropical terrains. Please welcome Len Kolff.
Thank you. Great, thank you and welcome everybody. It's great to be here and really exciting to run you through the Ewoyaa discovery, which is a hard rock lithium pegmatite project we discovered in 2016 and announced our maiden drilling results. I think it was 2018, and we've now just released our DFS. So it's been a really exciting story, and I've tried to put some slides together. First, just to set the scene about the project, what it looks like, and kind of the pitch we do in terms of the investment community, but that really tells some important lessons about the key aspects of the geology that drive the value of this project, and some of the key aspects about the geology and mineralogy in particular that drive processability, which is really important. And then once I've set the scene, I come back to kind of the discovery history of the project, how we found it, what are the key learnings, and how we're using those learnings to look for other projects within West Africa, which is a relatively new pegmatite field. As I said, this is the first time a hard rock lithium pegmatite's been discovered in Ghana, and the only other project in the region that has similar scale and similar mineralogy is the Goulamina project in Mali. That's now sitting at over 200 million tonnes, so it's a huge deposit. And there will no doubt be a lot more discoveries made within the Birimian of West Africa, but with the challenges of tropical weathering, since lithium is very mobile in the weathering profile. So yeah, here we go. This is our team in Ghana. And as you can see, Ghana is a fantastic place to work, very skilled labor force, workforce, especially in the mining sector. It's 100 years of mining history there. So not many expats other than Ewan that you can see in the middle there, our exploration manager. So great place to work. Okay, yes. There we go. So just a standard disclaimer. So just on the Ewoyaa project, so it's a hard rock spodumene pegmatite. The resource currently sits at 35.3 million tonnes at 1.25% lithium oxide. As I said, we've just put out our DFS that's delivered exceptional economics. We've got a major joint venture partner through Piedmont Lithium. They're an American NASDAQ listed company that are funding us through the studies and for a large portion of the capital cost of the build of the project. And they also have their hard rock lithium pegmatite project in Carolina in the US. And I'll talk through all the other key fundamentals of the project as we go through. So this is where the project's located. So not many places where you can find a mining project so close to the coast. So we're literally, where the Ewoyaa discovery was made is 4 kilometers to the ocean. You can actually see the ocean standing on the deposit. We're 100 kilometers from the capital of Accra. So it's like a 2-hour drive, depending on what the traffic's like. And then importantly, the deposit footprint's 110 kilometers to the operating deep sea port of Takoradi here. You can see here in pink, this is the Cape Coast batholith. So it's a large granite intrusion biotite granitoid. And then sitting within the margins of that granitoid are these embayments of metasediments. So these are Birimian mica schists, garnet schists, and staurolite schists. And then on this green side here, these are more mafic schists. And here's a separate pegmatite field as well, which hosts the Ejisamanku Hill lithium occurrence. Let's get to the next slide. So the resource here, total resource is now sitting at 35.3 at 1.25% lithium oxide. And you can see a large portion of that is in the high confidence category of measured and indicated. And you can see from a mining point of view, a large portion of that converts to reserve. So it's got good continuity, good modifying factors from a mining point of view, and that's all down to the processability, proximity to infrastructure, available workforce. So good resource to reserve conversion. So this is what the mineralization looks like. We've got two types of pegmatites in our project, what we call our coarse-grained P1 and our finer-grained P2. So very exciting names for those. But the lion's share of our mineralization is this coarse-grained P1. And I've got samples here of both types, so we can have a look at those in real life later. But what's important is all of our lithium occurs, well, 95% of our lithium occurs within spodumene, which are these green crystals here, and here in RC drill chips, and here in diamond core. It's very coarse grained. So the coarser the grain size and the more of your lithium credits that occur within spodumene, the better outcome you have from a processability. So it means you can more easily beneficiate and concentrate to a lithium concentrate or spodumene concentrate. SC6 is the terminology, so that's 6% spodumene concentrate, rather than having to go through flotation if you've got very fine-grained spodumene, or if you've got other lithium species there, such as petalite or eucryptite or lepidolite, which are all currently being mined in the market and processed downstream by the converters. But the preference for the converters is for a clean, coarse spodumene concentrate because it behaves well within the kilns, which is the first part of that conversion process. So this is good for us, and it's what drives down our OPEX and our CAPEX. And then this is what the finer grained P2 mineralization looks like here in outcrop. When we first saw it in mapping, this is back in 2016. We didn't have any experience in pegmatites exploration. We were actually working on gold projects, but we thought these were all granites. But when you took a closer look, you could actually see all these little blue crystals here. They're apatite crystals. And when we sampled it and assays came back, it's exactly the same grade as the coarse-grained spodumene pegmatite, but just very much finer grain. So it's a magmatic or kind of semi-hydrothermal process within the pegmatites, and we'll look later at what the distribution of these two different types of pegmatites looks like within the whole pegmatite, and it gives a bit of an idea about its possible origins in that regard. But you can see here the fine-grained P2 mineralization grading to a slightly coarser grained pegmatite. And here you can actually see spodumene crystals floating within a finer grained P2 matrix. And you can actually see that those crystals are starting to get re-ingested into that melt, so to speak. So the grade of this material here is also around about 1.2 to up to 2% lithium oxide, as is the grade in this material. So this would probably be high grade. This would probably be at around 2% lithium oxide. And then once it's concentrated, you'll get to that 6% concentrate value. But so it's amazing to see how that grain size variation, these are all just very fine spodumene crystals, and it provides or gives that same overall resource grade of 1.25. But from a processability point of view, this is much harder to process to a saleable concentrate than the coarse grain material. And depending on how much of that you got volumetrically would really dictate how you have to process the material going forwards. If you go into flotation at a much higher cost, or you can still generate a saleable product through a dense media separation circuit. So here's some cross sections of the pegmatite. So on the right here in red, you can see the 0.4 mineralization shells. So these are the pegmatites at greater than 0.4% lithium oxide. And in gray are the pit shells that have been designed around that. And then some cross sections through there. So this is what we call our main Ewoyaa trend, that north-south trend. And then you got these more east-west pegmatites, which is what we call our Abonku trend. Here in the grass cutter deposits, here in Ewoyaa Northeast and Kwesi Krom, Anochi, Abonku. So there are two main orientations, and this comes down to structural controls, which we'll see later. But interestingly, when you look at the cross sections here, you can see, so it's a subvertical feeder dike. And then in the Ewoyaa main section, so in this lens here, that's roughly 500 meters long and at surface 100 meters wide. So it blows out into this wine glass shape. And there are a few other pegmatites around the world that actually show this as well. So it must be something to do with those emplacement controls, structural controls, pressure, temperature scenarios around that emplacement. But quite interesting to see that same wine glass shape, which is also really useful from a mining point of view and strip ratios. But so you can see in white outline, that's the pegmatite itself. And then in red is the 0.4% outline. And then these blocks in here in green, this is the P2 mineralization, so that finer grained pegmatite, which we often see on the footwall contact of the pegmatite. And we only really see it in these north-south striking pegmatites. We don't see it in these east-west pegmatites, which are coarse-grained P1 from hanging wall to footwall. Now, this is an area, obviously, that we're trying to do more studies on and try to build a system where you can actually map P1 versus P2 from multi-element geochemistry or something else, because when most of this drilling is RC, and that's texture destructive. So you're not able, or it's hard to log grain size in your RC drill chips. And so we use diamond core, and now the guys have got their eyes in, they're actually getting better to pick up that coarse grain versus fine grain, but it's still not quantitative, it's qualitative. So that's something that we're trying to do some studies on, looking at multi-element geochem to see how we can really bed down that P2 mineralization. And then from a metallurgical test work point of view, this is really important for any pegmatites. So you can see here, these are each composites down individual drill holes. There's 64 in total. The blues, dark and light, are our P1, dark being fresh and light being transitional or that weathered material. And the greens are our P2 mineralization, again, dark, fresh, and light weathered. And then I've split these up by those mineralization trends. So this block here is our Ewoyaa main trend, that north-south trend, the P1s, P2s, weathered and fresh. And this block here is our Abonku east-west trends, again, weathered and fresh. And you can see there are hardly any P2 samples. It's the overwhelmingly coarse-grained P1. But so you can see the height of these bars is your recovery in HLS. So this is heavy liquid separation. And on average in the P1s, you're looking here at that 70%, but up to 90% recovery. And you're producing from a head grade, which is your brown dot here of around about 1.5 and up to 2%. You're getting up to a 6% concentrate easily. The red dots, that red line is 6% lithium oxide. And importantly, we also look at our iron concentration within that concentrate. You want that iron to be below 1%. The higher that iron is, it's a problem for the converters because it it actually starts to form a slag within the kilns. So every couple of weeks, they need to stop the kiln, scrape off all the slag on the inside of the kiln, and then start the plant up again. So they don't want to see iron in that concentrate at all. And the lower that is, the better your concentrate. So we're able to produce a high grade spodumene SC6 concentrate, and we've also demonstrated that we can convert that to hydroxide and carbonate, which was done here at ANSTO, but that's not really our focus. We're about producing a spodumene concentrate, and we're able to produce this concentrate through a simple DMS-only process flow sheet without having to go to flotation. When we dig down into the mineralogy of those concentrates, so here we can see a selection of those HLS composites, and this is the XRD analysis of those concentrates. So the more blue, the blue is spodumene, and then you can see all the other various lithium-bearing minerals and/or quartz, feldspar, muscovites. So it's predominantly made up of spodumene, quartz in yellow, and muscovite in grey. And then it's this last bit up here that hosts some of these other interesting minerals, but again, very small volumetrically. However, there are some samples here like this one where you can see the HLS recovery is significantly lower, and it does have volumetrically less spodumene within the concentrate, and some other minerals in here that you can see there, such as we've got lithiophyllite. We've also got amblygonite, which we got some samples of there, but overwhelmingly spodumene, so very clean mineralogy in that regard. So those characteristics, as I said, allow us to move to a DMS-only process flow sheet, which means low CapEx, low OpEx. So in our case, this project has $185 million CapEx. When you're talking about a flotation plant, so when a mine has to go whole of ore flotation, which then means it has a large amount of tails to deal with, much higher CapEx. You're looking at double that number for CapEx. If you're looking, for example, Pilgangoora projects, that's whole of ore flotation. Their CapEx was significantly higher to build that plant, and OpEx going forward is much higher. A lot more water use, a lot more energy use, and all of those tailings to deal with from an environmental point of view. So DMS is certainly preferred in that regard, and luckily for us, our project mineralogy allows for that. And then simple mining. So we saw the cross sections. So this is open pit mining operation from surface. I think the deepest pit goes to roughly 230 meters below the natural surface. Life of mine stripping ratio around 12:1. The early years much lower at 3-4 to 1. So a simple mining operation that's then scheduled to get that P1, P2 mix correct through the mill feed to maximize recoveries. And obviously from the trucking scenarios point of view. Then for any mining project, obviously logistics is key. Infrastructure. So our deposit is 1 kilometre to the Takoradi Highway, which is 110 kilometres to the operating deep sea port of Takoradi. So this is a dedicated minerals handling port. And then we've got grid power that actually runs over the widest part of the pegmatite. So if you couldn't have planned it better in that regard. But the power lines, which are fed by hydro from the Akasombo Dam, run over the deposit footprint. We actually need to relocate the power lines. And then finally, from an Africa point of view, or anywhere really, it's your social license to operate. And that's really important for us and something that we've started right from the beginning. So all Ghanaian team employ as much as where we can from the communities actually on the deposit footprint. We run regeneration nurseries to rehabilitate drill access and drill pads from an erosion control point of view, and support all of our communities in the project area. So all of that delivered these DFS metrics. We won't go into the details, but it's a 2.7 million tonne per annum run-of-mine operation that runs for 12 years with an NPV of over 1.5 billion US dollars, capital cost of 185 million and payback within 19 months. So that is really significant. And when you compare that to, say, a gold mine, you're looking at equivalent grades of 8 to 10 grams per tonne gold from a value point of view. And this is quite interesting when you look at the sensitivity in the study. So this is sensitivity to NPV. So our current NPV sits at that 1.5 billion. And then this is plus or minus 25% on the various levers. So you can see that the biggest lever that impacts NPV is the lithium price used in our study. Spodumene concentrates currently selling at around $3,500 US dollars per tonne. That's SC6. It's been as high as over $6,500 US dollars per tonne last year. But you can see that if you increase that spodumene price by plus or minus 25%, it does have a big impact on the NPV. It's still very healthy NPV at 25% below the $1,500 per tonne we used roughly in our study. The next one is the head grade. So obviously grades is king. The higher the grade of the material that goes through the mill, the better. And then recovery. So this is really important. So the better your recovery through the plant, and from our perspective, the better we understand the mineralization from that P1 and P2 perspective, the more important that is in terms of managing or improving your NPV. And then really when you come from that point downwards, you can see capital cost has hardly any effect on the NPV of the project. Normally, capital cost sits at the top here as the biggest lever on your NPV, whereas with spodumene projects, it's actually the opposite. It has hardly any impact, and that's because of this DMS process flow sheet, this very low CapEx project compared to a gold mine where you're building huge mills, huge tailings dams facilities, a much more complex flow sheet. So it's really telling, and then I guess ultimately it's that ore body knowledge that's driving this value, and it's important to get that right. Okay, so that's the overview of the project. So it set the scene, and now it's how did we get there? So really the story all started with somebody, I know Kevin Joyce. He was the managing director of a company called Birimian Gold. They were a gold explorer in Mali. So here we're looking at a geological map of the Birimian of West Africa. It's a paleoproterozoic terrain, and it's known for its gold endowment. Yet now it's proven that it's also highly prospective for lithium pegmatites. Typically, your pegmatite fields of the world are Archean age. So here in Australia, Archean. And now you're seeing in Canada a huge explosion of pegmatite discoveries being made there, LCT pegmatites, all Archean aged. The other known about field are Pan-African. So the Nigerian belts, East Africa, European belts. So these are much younger granitoids or tertiary granitoids. And typically the mineralogy of those pegmatites is more complex. So spodumene, lepidolite, eucryptite. And then finally, the Birimian is now proven as a prospective area to explore for pegmatites. But that was all not known about 6 years ago. Nobody would be exploring for pegmatites there. You just went there for gold. But Kevin Joyce here of Goulamina, of Birimian Gold at the time, demonstrated that the Birimian was highly prospective for pegmatites, and he made the Goulamina discovery at the time there with a main resource of 15.5 million tonnes. So this has now grown to 200 million tonnes. But with that, I thought, well, surely they don't just occur there. Where else do they occur? There's some simplistic models out there where you're looking on the margins of fractionated granitoids and then looking at those embayment zones and or structural zones and looking for those more fractionated fluids on the margins of the granitoids. And that was our original targeting rationale. Very simple, but when you dig deeper, and it's now certainly an area of detailed research, is do these pegmatites actually form from fractionated fluids out of the granitoids, or do they actually form by anatexis of the basement rocks? So, I mean, that doesn't impact, in this case, or then it didn't impact where we were looking. We were just looking, well, where else within the Birimian are there these fractionated granitoids and with tin, niobium, tantalum, beryllium, kaolinite, and or even spodumene or lithium occurrences recorded in the mineral occurrence maps. So that was the process, and literally just drawing circles, identifying those areas, highlighted the Cape Coast batholith and the southern coastline here, and our Ivory Coast portfolio. So that's what brought me into Ghana initially. And then we dug deeper. And through that work, I came across, and this was internet search, I came across this thesis that was done by this lady here, who I met last month in Ghana, through the University of Leeds in the UK in 1970. And her thesis was titled The Spodumene Pegmatites of Salt Pond, Ghana. So that was really tantalizing evidence that there were certainly spodumene-bearing pegmatites in this area, and what was enough to actually fly over to Ghana and to go to the geological survey that then helped us significantly, and in particular finding this report, which is an old archive report by the Ghana Geological Survey from work that they did in the region through the 50s, 60s, and 70s with a focus on kaolinite in the ceramics industry. But in there, they also recorded spodumene occurrences. But back then, there just was hardly any market for lithium. It was really used in medication and or greases, high temperature greases. So not really much of a focus. However, again, they'd done work, identified spodumene. So that was like the light bulb moment, bingo, let's go into the field and try and find these things. So Miss Samoka Mensah now, she's 84. She runs an environmental consultancy, but for our Ghanaian staff, it was a real, it was really exciting for them to meet her and an inspiration. So it's a really quite amazing story, I think. But so we then focus closer on the southern margin of the Cape Coast batholith, which is here. It's a biotite granitoid. And in particular, this embayment with metasediments, schists, and this area that's hatched red, which on the geological map is written up as an area of pronounced pegmatite veining. So this is where we focus further, and it took us a further year to find the pegmatites on the ground, because as I said, we didn't know what we were looking for. It's highly weathered, and sampling of lithium pegmatites at that time was a bit of a struggle. Labs hadn't really got it down packed in terms of their calibrations. So we had lab issues. We didn't really know what we were sampling. We could see there were white felsic rocks, but we didn't know what spodumene looked like, and especially when it's weathered. And then also the samples we initially collected were weathered, and they all came back at around 0.1, 0.2, not the 1 or 2% we were expecting from those geological survey reports. And that was all down to the fact that we were sampling weathered material and relatively small samples from a rock chip point of view. These are quite coarse grains, so you've got that nugget effect essentially to look out for when you're taking rock chips. So when we found out that lithium was very mobile, and certainly in this latitude, we went back to those areas and actually dug deeper in our trenches, resampled larger samples, and bang, reported these results. So from going from 0.1, 0.2% lithium oxide and nearly walking away from the project in 2016, 17, we announced these maiden results. And that's kind of this has now become our work process on the ground. So firstly, mapping, boots on the ground, is there's nothing more important than that. It's so important to get onto the ground and actually see the rocks. And now that we've got our eyes in, we understand better what to look for. And when you're lucky, you do find outcrops with visible spodumene. Not always, but we now understand what this starts to look like in more weather terrains and certainly within road cuttings or drill pad cuttings. But so mapping is crucial. And really it's just about rock descriptions as opposed to rock chips and looking for some of the telltales, in our case, apatite and or relic spodumene structures or fresh spodumene. We then we flew high resolution heli-borne geophysics, and in particular for radiometrics. We also grid our license area with soils, 100 by 100 meter soils. And we've set up an in-house lab with portable XRF and a handheld LIBS, lithium analyzer. And that lab has been running now for over 5 years, 6 years, and has assayed or analyzed in excess of 50,000 samples. We don't use it for resource estimation or in our drilling. It's really calibrated for exploration samples. Trenching and pitting we used to do. We don't do that anymore, just from a health and safety point of view. But it was really quite useful to see those weathering profiles and understand that more and know what spodumene looks like once it goes through that weathering profile. But we now do grid auger over our targets, which are identified from geophysics, soils, mapping, to then come in and grid auger them ahead of RC drilling. So here you can see our early lab. It's a bit more sophisticated now, but so we use a press to make pucks, and then we analyze them through our handheld XRF and the lithium LIBS analyzer. That's Andrew Summers there from SciAps, who some of you may know. But so this has been very successful for us and generates some really useful base maps. So we'll look into more detail on these, but this is our license holding. So it's 560 square kilometers with the Ewoyaa Pegmatite field sitting here and the Simandou Hill Pegmatite field sitting here. And you can see we're looking at, I think this one's rubidium in soils that we've covered to date. And this license, we're currently completing soils over now. So that's roughly another 10,000 soils to finalize. And here you'd be looking at roughly 30,000 soils. So when we look at these images more closely, so on the left, this is one of our outputs from the heli-borne geophysics. So this is potassium over thorium radiometrics. And then on the right here is lithium in soils. So you can see this feature here is very prominent. This is the Afrangwa granitoid. The Cape Coast batholith sits off the margin here, so you don't actually see that. But you do see these intrusive little granite bosses, which are granodiorites more so than granites. And it's around, they're highly fractionated, and we'll see some samples there. They actually have really characteristic textures of pegmatoidal granitoids on top of them. So they're really frothy on top. It's been historically the focus for feldspar mining for ceramics. But they may or may not be important for the Ewoyaa discovery, which sits here. Spatially, it's associated with it, but we don't know if genetically it's associated with it. You'd think it would be, given some of the textures we'll see. There's graphic intergrowth in feldspars, big feldspar crystals the size of this table, as well as these plumose, muscovite, chlorite intergrowths. Some really interesting textures, but we don't really know if they're genetically associated with them. They do appear, however, to be, when you look at the LIBS analysis, there's the lithium in soils. So you can see here, that's the Afrangwa granitoid. And then you see this very strong line running up and down there. That's actually drainage. So we think what the lithium libs, so, and then here, sorry, you can see the Ewoyaa deposit. So that actually does highlight in the soils. And we also pick it up as spot highs in tin, and it has a coincident rubidium anomaly in soils. So we use a combination of soils for lithium, tin, rubidium, potassium, thorium lows, in combination with radiometrics to circle areas of interest, and then to go onto the ground to the next stage, which is mapping and auger. But back to the libs here. So we've tried to understand what is, because these levels here, so the blues would probably be around the 0 to 100 ppm in soils through the libs. And then the greens around that 100 or 150 to 300 ppm. And then when you're on the pegmatites here, you're between 300 to 600, 700 ppm in soils. But this particular feature here, the Afranga granitoid and the Ekrabadzi granitoid here, they're sitting around 1,500 up to 9,000 ppm in soils. We've assayed rock chips, but we don't repeat those values. And what we actually think is happening is this is actually also full of mica, and that mica makes its way into the drainages, so it's a resistate. And then when we collect our soils in that fine fraction and then produce the puck, you're actually getting all those micas aligned. So you have this surface of mica that you're analyzing. And I think that's what's actually inflating the samples around Afranga and highlighting the drainages. Nonetheless, it is a targeting tool and it has worked for us. It's delivered multiple new discoveries that we've drilled and grown our resource over time. And it's a tool that we're still using now to explore the salt pond license out to the west here. So here we can see again the soils and the levels I spoke to about before. So the yellows are at that 1,500 up to 9,000 ppm. And then Ewoyaa itself, which sits here, is that 300-400 ppm to about 600-700 ppm in soils for lithium. So using those geophysics and then mapping on the ground to highlight our target areas, and then coming in with auger. So this has been a really invaluable tool for us. We've got anywhere between 2 up to 6 augers working day in, day out. It's also a good employment tool for the youth within the communities. So that really works in our favor and their favor as well. So the village elders and the traditional leaders are really pleased that we're employing a lot of the youth in that regard. But you can see here, so below the image below is a combination of rubidium and lithium in soils. And then in red are the mapped pegmatites to date, the current resource footprint predominantly in this area. And then the larger black dots is our resource drilling. So we've drilled 150,000 meters to date in roughly 800 holes. And then these finer dots here are all individual auger holes. So you can see we highlight an area of coincident geochem geophysics and then go into that area, map. And if we identify outcropping spodumene, it really prioritizes that target. Otherwise, it's just a grid auger drilling pattern. So this is like a corridor of anomalous results, as is this area here. And this anomaly here, which is the Crowfu target, which has lithium mineralization. But the auger is then used to see through the vegetation and the weathering profile to an average of 5 meters end of hole depth to actually discernible rock type. So we use it to map through that weathering cover, essentially. We do analyze those samples, but it's really to define the footprint of the pegmatite ahead of bringing the RC drill rig in to test that below weathering. So the better you can define and pinpoint that pegmatite footprint, the less money you'll waste trying to drill it with the RC drill rig. And so then here you can see, I guess it's our geological improvement, our understanding over time. So those initial discovery rock chips here back in May of 2017, and then ongoing trenching, the lines in blue, and our interpretation at the time, because you really don't get much outcrop. It's really, you could be walking through this secondary growth. It's all thicket secondary growth, mainly from charcoal and subsistence farming. But you could be walking down a cut track on the Orga, and there could be a spodumene outcrop literally 1 meter or 2 meters next to you, and you wouldn't see it. So it's really hard to try and put together that geology without the various data sets we've got now, and those early interpretations, you know, are limited by the points we had. So we had these trenches, some indications, and we thought we had a whole series of unechelon vein dikes. And then you can see our next interpretation with further points then move to a more fluid source or folded interpretation. Then we got drill access in and drill pads, and you can see it became more what we're looking at today, further drilling. And this extension to the north was highlighted, which actually goes through a valley. But then through further drilling, that then was identified as 2 separate unechelon lenses. So you can see that whole progression to where we are now over that, what is that, 5, 6 year period. This is quite telling. So the Geological Survey completed mapping as best they could, and stereo pair photo interpretation to try and interpret gross structural settings. And this is the mapping, their interpretation, which is really driven by the offset in these Emissian sediments. So these are much younger coastal sediments, and these are transverse structures coming off the Atlantic. And you can see where they actually occur. It does throw some light onto potential structural controls, and we're trying to build this up now with observation from our diamond drilling and structural measurements. But you can see this north-south accommodation fault that comes through here is closely associated with the Ewoyaa main emplacement. And then these unechelon east-west pegmatite dikes are more potentially associated with these northwest-southeast structures. So I think this is something that we're working on more now to understand, but it does provide some insight into the potential structural controls, which we then also feed into our exploration targeting. Just some views of the drilling. As I said, we're pretty lucky in Ghana, so several drilling contractors. I'd say 70% of our drilling is RC. Deepest hole we've drilled to date would be roughly 350 meters with RC. And 30% of our drilling is diamond core. We try and get a diamond hole on every drill section, at least one hole, for geological control, metallurgical sampling. And here you can see our drill spacings. So this is really dependent on your geology and continuity. But you know, we're looking at, what was it, 80 by 40 for inferred, and then we've infilled up to 20 by 20 for measured, and that holds well together from a variography point of view. And here you can see, finally, just a quick view of the various lenses. So here it's in plan, that main north-south trend, which is the Ewoyaa main trend, that's roughly 2.2 kilometers long there. And then the east-west pegmatites on those unechelon arrays up those northwest-southeast orientated structures. And then here, looking oblique, you can see the Ewoyaa northeast pegmatite swarm, Okwesi Krom, north and south. So a whole series of stacked vein dikes along that potential structural control. Likewise with the grass cutter pegmatites here. And looking north-south, the Ewoyaa main pegmatite, all generally subvertical. But then where we move into these sections where those two trends meet, we start to see the pegmatites on that north-south trend flattening out and becoming more sill-like. So these are areas that we're drilling currently, looking for extensions where those two trends meet to grow the resource out that way. And I think that's everything I've got there. So Yeah, I guess in summary, from an exploration point of view, geophysics has worked well for us. So it's regional targeting around fractionated granitoids and looking just in mineral occurrence maps for niobium, tantalum, tin, kaolinite, beryllium occurrences. And literally we just circled areas of interest on the basis of that. And then on the ground, high resolution radiometrics has worked for us, in addition to grid soils, but mapping should never be underestimated, because that has really been an important part of the prioritizing of our targets. But a lot of work to do still, and looking at now multi-element geochemistry more closely, and certainly as potential vectors for blind pegmatites or ones that are so weathered that you just don't get any indication of them at surface, but using multi-element geochem from Orgas to see whether or not there are any vectors in schists, or if you're coming over them that say, well, this is a fertile pegmatite. Because there are also a lot of barren pegmatites in these fields, so K-feldspar pegmatites as opposed to albite K-feldspar pegmatites. So it's how you tell those apart before you go and drill them, because you can waste money drilling a lot of barren pegmatites. So these are all areas that we're currently doing studies on and would like to continue doing studies on to improve our knowledge of these pegmatites. And that's it. Thank you very much.
Glenn, that was fantastic. Do we have any questions? If you're online, please raise your hand and we can elevate you. You can ask your question live or type it into the Q&A box. I have a question here from Mark Noppe.
Oh, he's going to throw a curveball in here.
No, I'm not, Lee. So I guess an observation and then just a couple of little questions. So I guess just an observation, if we were 100% spodumene in our con, we'd still only be 8% lithium oxide, right? So hence the 70-80% con gives you the 6%.
Correct, yeah. Lithium. So the 6% con actually originates from Greenbushes. It's just what Greenbushes was able to produce through their process flow sheet and what they've been selling into the market, and it's become the accepted name. Like iron ore has the lump or the high phosphorocnum blend, for example. It's just a volume of material that's been accepted by the market, and it's now become the gold standard. So SC6 is what Greenbushes could easily produce. Their head grade or their average resource grade is over 2%. It's exceptionally high grade, and they can continuously achieve that SC6. Whereas most new pegmatite projects coming into production now or in production, Pilgangoora, Bald Hills, Core, Sigma, just to name a few, they all are generally selling into the market around 5.5%. And you get a discount for that, but you're actually better off selling more volume at lower grade and taking that hit in the discount than you are trying to achieve 6%, which you can easily do in the DMS. You just dial up those density contrasts rather than trying to achieve DMS and losing recovery to tails. So you're better off selling more low-grade material in your concentrate and take that haircut rather than losing spodumene concentrate to your rejects.
Yeah, thanks. And I think just another contextual observation, you mentioned, plenty of pegmatites, but not all of them are prospective for potential economic extraction.
Yeah.
I read somewhere that probably way less than 1% of pegmatites are actually prospective with the right mineralogy. Is that the kind of ratio that you understand?
Yeah, that's the 1%. That's
of all pegmatites.
All pegmatites.
Way less than.
It could be in that order, because there are a lot of factors that drive. Notwithstanding, you need a highly fractionated LCT pegmatite, so that's one aspect. But once you do even have one of those fractionated pegmatites, what is the mineralogy? What is the grain size? What is the hardness of the pegmatite? That also drives the processability. You see. The hardness drives how much fines you generate through that primary crushing phase. And the higher amount of fines you generate through the crushing stage can dictate whether or not you need to go down a flotation flow sheet, even though you may have coarse spodumene. So this is the case in Pilgangoora. It has a high work index, and accordingly generates a high proportion of fines through that primary crushing phase. And that's driven them to go, well, rather than trying to have a more complex plant of DMS float, we're doing whole of ore float. And that's the same for Goulamina. So there are a lot of factors that dictate, whether it's an economic pegmatite or not. And yes, a large, or the lion's share of those pegmatites out there aren't LCT pegmatites, barren pegmatites.
Thank you very much. That was a great presentation. Lisa Forbes, flotation person. So when you talked about the estimates for the CapEx and the footprint of the flotation operations, was that done considering conventional treatment, or were you considering potentially looking at something like coarse fluid as flotation technology? Yeah, so our project, we're not considering flotation. So we are going DMS only process flow sheet. Yeah. But we do produce a middling stream from our DMS plant, which is, it comes out, so it's finer spodumene that hasn't fully liberated. It comes out at a similar resource grade around that 1.2%. And rather than currently in the market, you can sell that as what's called a DSO, direct shipping ore. But you're shipping low lithium credits halfway around the world, which seems crazy. But it has helped a lot of projects come into production whilst they build their processing plant and generate cash flow to start paying that capital back early. But in our case, we are now looking at we've just commenced a study to look at what the ability is like to process middlings through flotation, a flotation circuit. So it's a small volume, be a small footprint, but looking at those various options from a coarser grained flotation, so you're not going fine grained. And I understand that is currently out there in terms of a technology that's being used. It's very much out there, but also because the technology has found more popularity in mineral processing lately with their ability to process base metal ores. But the originally coarse particle flotation technology was developed for the not the phosphate space. Oh gosh, I'm drawing an absolute blank. For more of the oxide flotation space, for which spodumene is a lot more similar to. So that technology would be highly applicable.
Yeah, no, definitely, and certainly something that the study team is going to work on. Mm-hmm. And in addition to that flotation side, from what I understand, the chemistry of the water that you use is very important.
The phosphate space.
Yeah. So yeah, it's a fascinating area and will be another step for this project in terms of its financials. I'd love to talk more about that.
We are working closely with areas, so yes, we'll talk to you about that.
I think we have some questions online as well. So the first question is from Graham Rolfe. Is rubidium depleted in weathering as is lithium?
Less so. So no, we actually use it in our soils. And I think, again, that's because it's being picked up from those micas that are resistates.
And another question now from Craig Brown. What would be required to recover the feldspar as a marketable product?
Yeah, so that's something that we did actually include in our PFS, but haven't in our DFS because we haven't built or defined a feldspar resource. Which is one of the ASIC or ASX requirements around release of DFSs. But basically, it's a separate. You produce your spodumene concentrate at a certain SG cut in your cyclones, and then you adjust that cut in a subparallel circuit that focuses on the slightly less dense spodumene and produce a spodumene concentrate accordingly. And this is, I know certainly in Ghana or anywhere really, it means you're putting less waste in your waste dump. And it's a product that whilst in Europe, there's a market for it, but in West Africa, there's a growing market for it and a booming population. It's one of the fastest growing populous centers in the world currently, that coastline from Ghana to Nigeria, who are importing a lot of ceramics goods from Europe. Yet this mine the area will be able to produce a significant quantity of feldspar for use in ceramics. But it's just another cyclone at a different density contrast to produce a feldspar concentrate.
Wow. Sounds like there's plenty of additional potential there.
Yeah, I mean, from us, from the economics of the project, it helps reduce your OPEX, and dependent on the quality of the spodumene, which is something we're studying now, which is your sodium to potassium ratio, as well as your iron and or any other opaque contaminants. I've got my train of thought there. The pricing that ranges from anywhere from $25 a ton all the way up to $200-300 a ton for your technical grade feldspars that go into high temperature glasses, Pyrex, induction cooktops, as well as lithium for its heat resistance properties. But that's really driven by the chemistry of it, and in particular the contaminants, and that's down to your processing flow sheet and the original geology and mineralogy.
I have a question from Michael Cusson. He asks, you may have mentioned this, but do you have a tantalum niobium association? And if so, do you know what the relationship is with lithium?
Yeah, well, we don't. It's the pegmatite is remarkably monomineralic in that regard, from an economic minerals point of view. There are no tin credits, no niobium or tantalum credits. It's just spodumene, quartz, feldspar. And that does seem to be a bit of an association with the spodumene-only LCT pegmatites that you can process through DMS. But we do use tin and niobium, tantalum less so, but we do use that as one of our vectors in the soil geochem. So there is a slight, there is anomalism associated with those, but it doesn't produce an economic product.
We've got a question now from Steve Micklethwaite. The beryllium has a polyphase deformation history, and I noticed that some of your mapping of the pegmatites look like fold patterns rather than anything to do with transverse faulting. Have you investigated folding as an alternative structural model and ruled it out?
Yeah, no, it's a good question. We do see instances where pegmatites are likely propagating up folded schists. So the schists are quite tightly folded, isoclinally folded. And I'm sure that as well as cross-cutting dikes, we've got pegmatites that actually are strata bound, so to speak. But the emplacement zones of those broader bodies do appear to be associated with those more brittle structures that come through as a structural trap, dilation zone. But then when those pegmatites come through, they really do whatever they want to do. When you're drilling them, they're just like naughty children. They just go wherever they want to go. But it's finding those zones where you've got that good continuity. But we do see stringers and or those sills appear to be following or are foliation parallel in the schists.
I'm going to sneak in one.
Sorry, the pegmatites themselves are not foliated in any way. They're coarse, massive crystalline, other than where faults cut through them, so that they are not deformed or folded from what we can see in observations and drill core.
So I'm going to sneak in one of my own questions in between here. All of the techniques that you've described here for exploration rely on the pegmatite being outcropping and having weathered to some degree.
Yeah.
Is there anything that you could use to detect blind pegmatites, or in deep weathering terrains, is there, say, a depth of weathering profile that could be used with passive seismic or a tool like that to map these things out?
Yeah, so we trialed GPR, ground penetrating radar, but we weren't getting the energy attenuation into the ground. It was all just bouncing off the ground. And that's really down to your prep of the surfaces that you're dragging those GPR transmitters and receivers across. So it wasn't practical in our sense, and the depth that it could view was a bit limiting. But passive seismics, is something you would have seen in the press, and we're actually trialing it currently with Fleet. So it's exciting technology. It's using ambient noise. In our case, that noise is all coming from waves crashing on the ocean. So we've got a good noise source coming through. And then it's just looking at a velocity map. And this technology has been successfully used at Core Lithium. And there are a lot of other projects that are currently trialing passive seismic. So we're going through that process currently, specifically to look for blind pegmatites or shoulder pegmatites that we just haven't pushed the drill hole further to test and just miss them.
Oh, excellent. Well, I'm afraid that's all we've got time for this afternoon. Thank you very much for a fascinating talk.
No, thank you. Got a load of rocks here, if anybody wants to see them.
Yeah, this is one of the benefits of coming in and seeing these in person, as Len's brought an excellent collection of lithium ore and rock samples in to look at. But if you'll join me in thanking Len one more time.